Hello students! Today we are going to discuss the concept of energy levels. And we will start by considering the simplest of all atoms, the hydrogen atom, consisting of a single proton as the nucleus and one orbiting electron. If we imagine the electron orbiting the nucleus just like Earth orbits the Sun, for instance, I think this will immediately start you off on the wrong foot. In fact, even this diagram is grossly misleading since it shows a nice circular orbit. The motion of the electron is actually rather unpredictable, and we can only say where it is most likely to be, meaning that we can only say where there is the highest probability of finding the electron. And this is very different from planetary motion, where we can predict with great accuracy the position and time of an orbiting planet. But for the time being, I'd like to concentrate on a persistent problem that intrigued most scientists around the year 1911. The fact that orbiting electrons were ultimately accelerating charged particles. According to established theory of electromagnetism, these electrons were expected to emit radiation continuously, just as any accelerated charge would do. Owing to their loss of energy, the electrons would necessarily spiral down into the nucleus, and the whole atom would shrink. Something which clearly does not happen in practice, otherwise objects around us would practically vanish out of sight. So, what were scientists missing at the time? The breakthrough came in 1911 from the Danish physicist Niels Bohr, who suggested that the atom can only exist in certain fixed energy states called energy levels, corresponding to particular electron orbits. This model of the atom is in fact referred to as the Bohr atomic model. If we keep in mind the hydrogen atom, in other words, this means that the orbiting electron cannot have any value of energy, but only specific ones. We say that its energy is discrete or quantized, which in other words means not continuous. This concept perhaps can be understood if we consider the analogy of the ramp versus stairs. If we imagine a box pushed up a ramp, then it could possibly have any value of gravitational potential energy, since it can be at any height with respect to the floor. However, on stairs, the box can only have specific values of energy, and hence, in situation B, we say that the energy of the box is, as we're saying, discrete or quantized. Energy levels are represented by horizontal lines as shown in this figure here. Each energy level is assigned a number called the quantum number. Note that the number of energy levels is infinite. Each line represents a possible energy value that the electron can have. Which is shown here in electron volts. Note that the energy gap or difference between the various levels is not equal. These values belong only to the hydrogen atom. So if we had to consider another element, its atom would have a completely different set of values. Of course, you do not need to know any of these values by heart. The first energy level is the lowest and most stable energy state. On its own, and without any outside intervention, the electron would occupy this level, which is called the ground state. As we move up to the higher energy levels, the energy value increases progressively. Now, you may have noticed that the energy values are negative. You should not let this to confuse you. Energy was and still is a scalar quantity, so why negative? Let us shift our attention to an energy of 0 electron volts. This value of energy, rather than representing the minimum energy, is assigned to the infinite energy state as a maximum. In fact, it is at the very top of the energy ladder. We will come to its significance shortly, but for the moment, please understand that if 0 electron volts is a maximum value of energy, then obviously all the lower energy levels must be negative. Also, let me remind you that you may convert between electron volts and joules using this constant here. So, focusing again on the hydrogen atom, particularly on the single electron it contains, we are saying that on its own, this will be found in its most stable state with an energy of minus 13.6 electron volts. The next possible energy state is that of minus 3.4 electron volts. Any value in between these two is not possible. But how can the electron get promoted from the ground state to the second energy level? This is only possible if the electron gains the exact energy difference between the two levels, which in this case would be 10.2 electron volts. So the energy difference E2 minus E1 is equal to minus 3.4 eV minus 13.6 eV, which gives 10.2 electron volts. So that is the energy difference between the two energy levels, n equals 1 and n equals 2. But how can the electron gain this energy? Well, there are a couple of possible mechanisms. The atom could be subjected to bombarding particles, meaning highly energetic particles incident onto the atom. Otherwise, the atom could be exposed to electromagnetic radiation of the right frequency value. And what do I mean by the right frequency value? You must recall that in previous lectures, we discussed how electromagnetic radiation may be considered as a stream of photons, each of energy given by HF. Thus, if we had to expose the hydrogen atoms to electromagnetic radiation of frequency 2.47 times 10 to the power of 15 Hertz, this would mean that each photon will have exactly the right amount of energy, that is 10.2 eV. The working is shown here, and it is very straightforward. So we're saying that E is equal to HF. So F is E on H. Now the energy in this case is 10.2 electron volts multiplied by this value to convert it to joules and divided by Planck's constant H, which gives us the value of the frequency of electromagnetic radiation, which would ensure that its photons carry exactly this amount of energy, 10.2 eV. So what happens when we expose hydrogen atoms to this kind of frequency? So there will be a high probability that some hydrogen atoms will absorb a photon, and consequently they will get promoted to the second energy level at a value of minus 3.4 electron volts. I repeat that anything in between these two energy states is not possible. However, having said that, we could get a transition directly to the third energy level. You can see that the energy difference is now 12.1 electron volts. And if we repeat the same calculation we did previously, we would find that this now corresponds to electromagnetic radiation of 2.93 times 10 to the 15 Hertz. The working is similar and is shown here with an energy value of 12.1 electron volts, giving 2.93 times 10 to the 15 Hertz. Now, what if the electron gains 13.6 electron volts? If the electron in the ground state at minus 13.6 electron volts gains 13.6 electron volts, then it is clear that this would promote the electron to the infinite state, meaning that it would gain sufficient energy to break free from any influence from the nucleus. The atom would now have an electron less, and with an electron less, the atom thus becomes an ion. In fact, this energy is not surprisingly called the ionization energy, and is defined as the minimum amount of energy needed by an electron to just become free. And why minimum? Because, of course, it could gain even more energy than this value. The excess energy would appear as kinetic energy of the now free electron. And it is important to note that the energy of a free electron is no longer quantized, which means that it can now have any value of energy. Now, when an electron gets promoted to the second or higher energy levels, the atom is said to be in an excited state. This means that the atom has excess energy and is thus unstable. In fact, we find that almost immediately after absorbing energy, and we're talking within 10 to the minus 8 of a second, the atom loses this energy by emitting electromagnetic radiation, and subsequently, the electron falls back to a lower energy level. This diagram shows the various possibilities for the electron in a hydrogen atom to fall back to a lower energy level. Each transition is accompanied by a loss of energy in the form of electromagnetic radiation, meaning that the hydrogen atom loses energy by emitting electromagnetic radiation of a particular frequency. And this explains the emission line spectra we discussed in the previous lecture. Let's take, for example, this transition from n equals 3 to n equals 2, forming part of the so-called Balmer series. By the way, I emphasize that you do not need to know any of these series by heart. So a transition from the third to the second energy level is accompanied by electromagnetic radiation of wavelength around 650 nanometers. And this is calculated as follows. So the energy difference between the second and third energy levels is 1.9 electron volts. But we know that this change in energy is equivalent to HF or Hc on lambda, since F, the frequency, is c on lambda, where c is the speed of light, 3 times 10 to the 8 meters per second, h is the usual Planck's constant, and the change in energy is 1.9 electron volts multiplied by this conversion factor here to convert it in joules, and this gives a wavelength of around 650 nanometers. So we're saying that the red line in the emission line spectrum of hydrogen corresponds to a transition from the third to the second energy level. And it is the same thing with all the other possible transitions. The only difference would be that the emitted electromagnetic radiation does not necessarily lie within the range of visible wavelengths. In fact, in the case of hydrogen, we can observe just 4 with the naked eye, the ones I'm showing here. These correspond to transitions in the Balmer series. All the others are outside the visible range, and as we're saying, we cannot observe them with the naked eye. And we are now in a much better position to understand and appreciate the importance of emission line spectra, since these are experimental evidence that the energy of orbiting electrons is really quantized. Bohr's model of the atom was a tremendous success in explaining the spectrum of the hydrogen atom. Unfortunately, when the mathematics of the model was applied to atoms with more than one electron, it was not able to correctly predict the frequencies of the spectral lines. While Bohr's model represented a great advancement in the atomic model, and the concept of electron transitions between energy levels is valid, improvements were needed in order to fully understand all atoms and their chemical behavior. But with regards to your syllabus, these concepts are just what you need to grasp. In the next lecture, we shall be discussing the concept of wave-particle duality. Bye-bye.